Hi, so this is the second part of the third video in the forces section and about friction. So this is the sort of last major concept in the sort of linear forces area. A little bit of a tricky one to get your brain round at first. What is it? Friction. Friction is a force that opposes motion and acts along the plane where the motion or tendency for motion occurs. So in this situation here, if we've got this particle on this surface and we're pulling away with a force of p newtons, let's say this thing isn't moving, therefore there must be an opposing force, an equal and opposing force, and that is the friction. So we took it away, but we haven't made it move as yet. So so we sometimes call it a balancing force. So then if we just carry on pulling a bit harder and a bit harder, well, that can't go on forever, and eventually this box, this crate, whatever it is going to slip. And the reason for that is we've actually reached the maximum friction. So friction will increase as a balancing force while it's in equilibrium, but there's a limit. And at that limit, it starts to move and it will accelerate. So that limit is the maximum friction. Okay, well, the maximum friction, we can calculate this, and how do we calculate it? Well, it depends on two things, really. No surprise. First of all, it's the roughness of the surfaces. So if you're dragging something smooth across a skating rink, then obviously there's not going to be very much friction. The other thing is, or you might think in terms of the weight. We describe that in terms of the normal reaction. So, which is it's a sort of feels a bit like the net weight in many situations. So we can actually calculate that maximum friction, and so basically it's this little equation, which is maximum friction. I tend to denote this by Fx just to distinguish it from the friction that is balancing the whatever the pulling force is, times the coefficient of friction, which we denote with the Greek letter mu, times the normal reaction. So yeah, as straightforward as that, really. That little calculation. Now this mu, this coefficient of friction, actually varies between 0 and 1. So 0 means very slippy, two very slippy surfaces, or at least one very slippy surface, and 1 would be totally rough and very difficult to get any movement at all. Okay, so let's just kind of work that through a little bit more. So here we've got a mass of 10 kilograms sitting on a horizontal surface. It's got a weight of 10 newtons acting on it due to its own weight, and therefore a reaction force of 10 G. We've no motion in this vertical direction, so these two forces must balance out. I've defined we've got a coefficient of friction of 0.6 here, force pulling it forward, friction pulling it backwards. And in this situation, well, Fx equals mu r. So here we're just calculating our maximum friction. So that's 0.6 times the reaction force, which is 10 G. So the the maximum friction is 6G, Newton, 16 Newtons maximum friction. So as we pull this, if we start off at with a force of 1G, just gradually increase it, well, it's going to get to 6G, and at 6G, it is on the point of slipping. We get to a fraction more than 6G, and then it starts to, it slips, and it accelerates because there is a net positive force in the right direction, and that net positive force we take as being P minus Fx, maximum friction. So the difference between the two. Now, to say this is very much what we do at A level. It's a slight simplification. I think if you go into sort of high levels of mechanics and physics, you find that there is a distinction drawn between static and dynamic friction. We're kind of not really interested in that at A level. What we do is a slight simplification, and we say that once the particle has started accelerating, then there is a sort of constant opposing force, which is equal to the maximum friction Fx. So that is the concept. So let's just move on and illustrate that with an example. Here we go. So a box of mass 30 kilograms is being pulled along a rough horizontal ground at a constant speed. This is interesting. A constant speed. So we could call this an equilibrium problem, but anyway, this will come a bit clearer. Using a rope, the rope makes an angle of 20 degrees with the ground, and the coefficient of friction is 0.4. Box's model as a particle, rope as a light inextensible string, usual disclaimers, and the tension in the rope is P newtons, so we've got to find the value of P. Okay, so I've drawn my diagram down here, and I know I've cheated, I've done a bit of copying, and that's why I've scribbled out this this N here, because I don't like units in my diagrams. But we've completed the forces diagram. We've got this this weight of 30G. That's giving us first of all, let's have a look at the horizontal forces. So this P result horizontally is giving us P cos 20, and then we've got our opposing force. Now because it's at constant speed, it's already slipped. It's already gone past the point of slipping. So therefore, the friction is at the maximum friction. So this is a kind of code really for saying, use the maximum friction. Right, so in the vertical direction, we've got the resolved part of P going vertically, P sine 20. We've got the weight downwards, and then we've got the reaction force upwards. So looking vertically, we've got we can actually solve for R, and that's what we've got here in this equation here. R plus P sine 20, the upward forces, equals 30G, the downward force, and then rearrange that, we get this. Okay, so then also looking at our maximum friction equation, we've got the maximum friction is equal to the reaction force times the coefficient of friction. Okay, so what we're trying to solve for is P here. We can see from this, or from the horizontal here, that f of x equals P cos 20. So basically, I've knocked the maximum friction out of the calculation. So instead of f of x equals mu times r, what I've done is I've used P cos 20, which is f of x. Okay, so that's essentially the same as f of x equals mu times the reaction force. Okay, so now we've got a nice fully formed equation. only one unknown. I mean, all these things are known. That's known. We know these two. We know sine 20. We know mu. So essentially, we just have to do a bit of reorganization now. P on its own, explicit in P. Work that through. I'll not go through the algebra. Essentially out the bottom pops this. P is 111.5 newtons. That's to 1 decimal place. And as I've said, always when we're rounding, always put the accuracy that you've rounded to 1 decimal place. So that is basically it. So that's kind of quite a nice little illustration of how friction, maximum friction, is calculated, and hopefully that's been useful. Okay, so I think armed with that, you've got all the 3 main concepts, so should be in a good position to have a go at some linear forces problems. Okay, so in the next video, we'll be looking at moments. So we're looking at rotational forces in equilibrium. So I'll see you in the next video.